Hi everyone, so in this video we're going to talk about velocity equations. This is really just an extension of the vector equation of a line that you've already seen, but it's with the specific application of velocity, which is a very common use for vectors. Okay, so as you will already know, velocity is a vector because it has magnitude and direction, and the magnitude of velocity is the speed. So what do I mean by that? Let's see that in real life. For example, 10 meters per second north is different from 10 meters per second east. 10 meters per second is the speed, 10 meters per second north is the velocity because it has a speed, a magnitude, and a direction north. Okay, so for example, we have a boat at point 4,1 and it's moving at a velocity of -3I plus j kilometers per hour, and we're asked what is the speed of the boat. Okay, first of all, let's just visualize what's happening. So if we imagine on a set of XY coordinate axes, these define the position of the boat, and we have some boat, let's say here, this is boat A, and we're told that's at 4,1. And it's moving at a velocity of -3I. So it's moving something like this, where every hour it does -3 in this direction, 1 in this direction. Okay, and it keeps moving along like that. So question 1, what is the speed of the boat? Well, my speed is just the magnitude of my velocity, and my velocity is -3,1. So I can simply write that as the square root of -3 squared plus 1 squared. And that's just going to give me the square root of 10. So that's my speed. I should write kilometers per hour. Okay, question 2. What is the position vector of the boat after 1 hour? Well, it starts down here at 4,1, and then we said it's moving at -3,1 kilometers per hour. So every hour it moves -3 in the x direction, 1 in the y direction. So after 1 hour, its position, let's call that R1, is just going to be its original position. So its initial position, 4,1, plus that velocity vector of -3,1. And that will just give me a position of 1, 2. Okay, question 3 is asking me the position vector of the boat after t hours. So it wants a general expression for the position vector of the boat. So my general position vector, well, it's starting, like we said, at 4,1 here, and then every hour it moves -3,1. So we said after 1 hour, we just added one lot of -3,1. You can imagine after another hour, it will have moved another -3 and up another 1. And after 3 hours, it will do the same thing again, etc., etc. After t hours, it will have done that t times. So I can simply say that the position vector after t hours will just be its initial position plus t lots of that velocity vector -3,1. Okay, why is that useful? That's given me an expression for the position vector after a certain amount of time, given its initial position and its velocity. So this gives us a general expression for the position vector of an object, which we can see here. The position vector is given by its initial position plus its velocity multiplied by the amount of time that's passed since it was at its initial position. That is just the vector equation of a straight line in the context of velocity. Okay, so let's have a look at using that in context. So, for example, we have a boat with position vector 4i at 12 o'clock. Sorry, 4i 5j at 12 o'clock. And 2 hours later, the position vector of the boat B is at 2i plus 12j. Okay, we are asked to find the velocity of B. So this time we are given the initial position and a position later, and we're trying to find the velocity. Well, this is just like substituting into a normal algebraic equation, trying to solve for an unknown. In this case, the unknown is the vector of velocity. So I can write out my general expression for a position vector. It's the initial position plus the velocity multiplied by t. And let's substitute in what we know. Well, we know that the initial position is 4, 5. We don't know its velocity. We want to find its velocity. And we know that 2 hours has passed. So that's going to be 2 times the velocity. And the position vector after 2 hours on the left-hand side is 2, 12. Okay, and I can just rearrange that as I would do with algebra. Let's take away 4, 5 from both sides, and that's going to leave me with -2, 7. And therefore, my velocity, if I divide by 2 both sides, will be -1, 3.5. So that's my velocity of B. They haven't given me any units, so I don't need to include any. Okay, question 2. Find an expression for the position vector of B, t hours after 12 o'clock as a single vector. So now it just wants a general expression for the position vector. Now that I've found the velocity vector, again, I can write out my general expression. And now I can substitute in what's always true. So for every case, if I'm trying to find the position vector, it's going to be starting at 4, 5, plus this velocity, which is -1, 3.5, which we found in part 1, and multiplied by the time. Be careful, it does ask for it as a single vector, so I just need to combine that into one vector, so 4 minus t, just combining the x and y components separately, and 5 plus 3.5 t. That's it. Okay, I suggest you practice a couple of these. There is a couple more little bits of information that are particularly useful when manipulating things to do with velocity and vectors. So we have these things called unit vectors. They are just vectors with length of 1 unit. And we can scale vectors to get, or rescale vectors to change their magnitude while we keep the direction constant, and that's how we get our unit vectors. Okay, what do I mean by that? If we have some vector here, A, and let's say that the length is 7, so we can say the magnitude of this vector A is 7. Well, if I want the unit vector of A, let's draw that here, and I'm just going to call that A hat. That is in the exact same direction as A, so parallel to A, but it has magnitude 1. So I could get the unit vector of A by scaling it down by a factor of, in this case, 7. So just dividing my vector by 7 or dividing it by the magnitude. So I can write generally my unit vector, we called that A with a little hat, is going to be your original vector, so A, divided by, in this case it was 7, whatever the length is. So let's write that generally, the magnitude of A. So that's how all I'm doing is I'm rescaling the vector, dividing it by its length, so it's the same direction, but with a length of 1. Why is that useful when we're thinking about velocity? Well, often when we're talking about velocity, we use the speed for the magnitude. So we're given the speed, which is the length of the velocity vector, and then we're given a unit vector which defines the direction. So we can define the speed and the direction separately when we're talking about velocity. Okay, so how can I think about that in practice? So for example, if we have a vector that defines the direction of some velocity, and let's say again that's the vector A, and let's say we know that the speed of this object is, let's say, 12 meters per second. Okay, and I should denote that as v. Okay, so I have a speed and I have a direction. Note that this direction vector here, this is not a unit vector. So I'm just saying this is some vector that's in the same direction as the velocity. If I wanted to find the velocity, I would just need to take the speed and multiply it by the unit vector of A. because I'm saying I know it's in the same direction as A, and I know that it has a length of 12. So if I can take something in the direction of A that's just 1, so let's draw that down here, say this is the unit vector of A, length 1, and I multiply that by 12, that will give me my velocity. So if it's helpful, I can write up here, the velocity is 12 in this specific example, times the unit vector. And let's substitute in what we already know up here about how we find a unit vector. All we're doing is we're taking the direction vector and dividing it by its length so that we get something of length 1, and then we multiply that by the actual length we want, the speed. Okay. So let's have a look at that again in context. So we're told a ship has a speed of 8.5 meters per second in a direction parallel to 4i plus 3j. Find the velocity vector. Okay, so note, just like in that previous example, we've got the speed, and this is effectively our A. It's not a unit vector, but it's the direction in which our velocity is acting. Okay, so we want to find the velocity, and we know that that is the speed multiplied by the unit vector in the direction of A. And we know we can write that, well, that's going to be the actual vector A divided by the vector A's length. That will rescale it to a length of 1. Okay, which means we need to find the magnitude of A. So A, if you find it helpful, I always find it helpful to write it in component form for 3, and therefore the magnitude of A is going to be the square root of 4 squared plus 3 squared, that's 5, and therefore this unit vector, which is the vector A divided by its length, is just going to be dividing by 5, so 1/5 of 4, 3, and that's just, again, you're just dividing each component separately, same as multiplying by a scalar, 4 out over 5 and 3 over 5. Okay, now that I have this, I can calculate my velocity. All I need to do is I need to substitute in my speed, which is 8.5, and this unit vector. So my unit vector is just 4 out of 5. If you want to write it as 0.8, you can. 4 out of 5 divided by 3 over 5. So that's just going to be 8.5 times 4 over 5 is 6.8. And 8.5 times 3/5 is 5.1. Okay, and that's my velocity vector of the boat. Again, we are given units, so we should include them, meters per second. Okay, the last little thing to do with velocity is relative position. Again, this is nothing new, it's just a different application of what you've already seen. So the relative position just gives the position of an object relative to another object, rather than position vectors, which give the position relative to the origin. So if we think about, again, anytime you can draw your vectors on a diagram, it's incredibly useful. So let's say we've got some object A here and some object B here. Okay, now each of these objects have some position vector relative to the origin. So position vector of A and a position vector of B. And I'm interested in the relative position. So I'm interested in this vector. I haven't put an arrow on yet because it's incredibly important you read what the question is asking for. So in this specific example, I'm asked for the relative position of B from A. So I'm going from A towards B. So it's just going to be the vector AB. So that's the relative position of B from A. It's just my vector AB. Okay, so if you can imagine I want to go from A to B, you can imagine by basic vector addition, I'm going minus RA plus RB. So I can write this as minus RA plus RB, or just RB minus RA, just basic vector addition. And if I then wanted to figure out the distance between A and B? Well, that's just going to be the magnitude of this vector. It's just that length there. It's the magnitude of that vector AB. So I can write it as the magnitude of AB. Okay, so again, let's see that in context. So we're given the example of two boats, A and B, have position vectors given by the velocity equations below. Again, just the vector equation of a straight line. All distances are in meters. Show that the two boats do not collide. Okay, so in order to do that, we need to think carefully about what it means for the two boats to not collide. If the two boats don't collide, it means that when their x coordinates are the same at some time, if their y coordinates are also the same, they'll collide. If their y coordinates are not the same, they won't. If you can imagine on a little diagram, let's say at their x coordinates are the same at some time here, and I've got my boat here, A, and if the y coordinates are the same, so let's say B is directly on top, they're obviously colliding. However, if their y coordinates are not the same, but their x coordinates are the same at this specific time, for example, if it looks like this, then they won't collide. So we're going to find the time at which their x coordinates are the same and then see if their y coordinates are also the same. Okay, so part one. So when the x coordinate of A is equal to the x coordinate of B, we're going to try and find that time. It's often useful when you're working with calculations like this with x and y coordinates. You might prefer to write your position vectors as one vector. So 2 plus 2.5t and 5 minus 3t. And for the position vector of B, 3 plus 2t and then minus 1 plus t, just so you can really see the x and y components of each of the vectors. Okay, so now my x coordinate of A, well, that's 2 plus 2.5t, and that's going to be equal to 3 plus 2t. So I'm solving for t to find the time at which their x coordinates are equal. If I solve for t, use nsolve, use algebra, whatever you want, it gives me a time of 2. Okay, then I need to find at this time t equals 2. What are the y coordinates? The y coordinate of A, well, I've got the expression 5 minus 3t. That's this part up here. So 5 minus 3 times 2, that's going to give me minus 1. And the y coordinate of B is equal to minus 1 plus t, so minus 1 plus 2. That gives me 1. Okay, so I can see at t equals 2, when the x coordinate of A is equal to the x coordinate of B, the y coordinate of A is not equal to the y coordinate of B, so the boats do not collide. That final conclusion, that sentence, is incredibly important and will be worth a mark if you're working through a question like this. Okay, let's take a look at question 2. So we're asked to find the shortest distance between the two boats at the time at which, and the time at which this occurs. So if we flip back to that relative position idea, well, the distance between is just given by the magnitude of the relative position vector. So we need to find the relative position. So part 2, the relative position between A and B, well, in this case, we're finding a distance eventually, so it doesn't really matter whether we're going A to B or B to A, because we're not asked for a relative position vector as the final answer. So I'm just going to go, the relative position of B from A is the vector AB. And that is, we said, the position vector of B minus the position vector of A, just by basic vector addition. Okay, and I can substitute in what those actually are. So 3 plus 2t minus 1 plus t minus 2 plus 2.5t and 5 minus 3t. And again, I'm just combining the x component along the top. So that's going to give me 1 minus 0.5t. And along the bottom, I'm going to get minus 6 plus 4t. So that's my relative position vector of B from A. That's not what I want. I want the shortest distance, so I want an expression for the distance between the two boats, which is just the magnitude, the length of that vector. Okay, and we know by Pythagoras that's just the square root of the square of each of the components summed, so 1 minus 0.5t squared plus minus 6 plus 4t squared. Okay, now what you'll notice is we're trying to find here this magnitude, but we've got an unknown. We can't just solve it because this is a function. This is an expression for how you find the distance between the two boats at any specific time. And we want to find when that is the shortest, so when that's the minimum. Well, I've just got a function and I want to find its minimum. So I can plot on my graphic display calculator, make sure on your workings you show a quick sketch. Not sure what that function looks like. I sketch it on my calculator. I see it looks something like this. This is t. And there's an obvious minimum, which from my calculator I can read as 1.51 and 0.248. Now the question asks me for the distance between the shortest distance between the two boats and the time at which this occurs. So the shortest distance is equal to, well, the distance is my y coordinate, 0.248, in this case meters, because we're told all distances are in meters. And this occurs at time t is equal to 1.51. And just to check, we're not given a unit for time, so we can leave it like that. Okay, so I suggest you have a go at some of the questions on velocity equations.